Welcome back. So I've started this video lecture series on reinforcement learning, and the last three videos were at a very high level, kind of what is reinforcement learning, how does it work, what are some of the applications, but we really didn't dig into too many details on the actual algorithms of how you implement reinforcement learning in practice. And so that's what I'm actually going to do today and in this next part of this series, is something I hope is going to be really, really useful kind of for all of you, which is the first thing is I'm going to kind of organize the different approaches of reinforcement learning. So this is a massive field that's about 100 years old, right? This merges neuroscience, behavioral science, like Pavlov's dog, optimization theory, optimal control, think Bellman's equation and the Hamilton-Jacobi-Bellman equation, all the way to modern day deep reinforcement learning, which is kind of how to use powerful machine learning techniques to solve these optimization problems. And you'll remember that in my view of reinforcement learning, this is really at the intersection of machine learning and control theory. So we're essentially machine learning good, effective control strategies to interact with an environment. Okay, good. And so in this first lecture, what I'm going to do, and I'm hoping that this is actually super useful for some of you, is I'm going to talk through the organization of these different decisions you have to make and kind of how you can think about the landscape of reinforcement learning. Before going on, I want to mention this is actually a chapter in the new second edition of our book, Data-Driven Science and Engineering, with myself and Nathan Kutz. And reinforcement learning was one of the new chapters I decided to write. So this is a great excuse for me to get to learn more about reinforcement learning. And it's also a nice opportunity for me to kind of get to communicate more details to you. So if you want to download this chapter, the link is here. I'll put it in the comments below, and I'll have a link to the second edition of the book up soon as well, probably in the comments. Good. So a new chapter, you can follow along with all of the videos, and each video kind of follows the chapter. Good. So before I get into that organizational chart of how all of these different types of reinforcement learning can be thought of, I want to just do a really, really quick recap of what is the reinforcement learning problem. So in reinforcement learning, you have an agent that gets to interact with the world or the environment through a set of actions. Sometimes these are discrete actions, sometimes these are continuous actions. If I have a robot, I might have a continuous action space. Whereas if I'm playing a game, if I'm the white pieces on a chessboard, then I have a discrete set of actions, even though it might be kind of high dimensional. And I observe the state of the system. At each time step, I get to observe the state of the system and use that information to change my actions to try to maximize my current or future rewards through playing. And I'll mention that in lots of applications, for example, in chess, the reward structure might be quite sparse. I might not get any feedback on whether or not I'm making good moves until the very end when I either win or lose. Tic-tac-toe, backgammon, checkers, Go are all kind of the same way. And that delayed reward structure is one of the things that makes this reinforcement learning problem really, really challenging. It's what makes learning in animal systems also challenging. If you want to teach your dog a trick, they have to know kind of step by step what you want them to do. Steps to train a behavior. And so the agent, their control strategy or their policy is typically called pi, and it basically is a probability of taking action A given a state S, a current state S. So this could be a deterministic policy, it could be a probabilistic policy, but essentially it's a set of rules that determines what actions I as the agent take given what I sense in the environment to maximize my future rewards. So that's the policy, and again, usually this is written in a probabilistic framework because typically the environment is written as a probabilistic model. And there is something called a value function. So given some policy pi that I take, then I can associate a value with being in each of the states of the system, essentially by what is my expected future reward, add up all of my future rewards, what's the expectation of that, and we'll put in this little discount factor because future rewards might be less advantageous to me than current rewards. This is just something that people do in economics. atomic theory. It's kind of like a utility function. And so for every policy pi, there is a value associated with being in each of the given states S. Now, again, I'll point out, for even reasonably sophisticated problems, you can do this for tic-tac-toe. You can enumerate all possible states and all possible actions, and you can compute this value function kind of through brute force. But even for moderately complicated games, even like checkers, let alone backgammon or chess or Go, this state space, the space of all possible states you could observe your system in, is astronomically large. I think it's estimated that there's 10 to the 80 plus, maybe it's 10 to the 180, I forget. It's a huge number of possible chessboards, even more possible Go boards. And so you can't really actually enumerate this value function. But it's a good kind of abstract function that we can think about, are these policy functions and these value functions. And at least in simplistic dynamic programming, we often assume that we know a model of our environment. And I'll get to that in a minute. So the goal here, the entire goal of reinforcement learning, is to learn through trial and error, through experience, what is the optimal policy to maximize your future rewards. Okay, so notice that this value function is a function of policy. Pi, I want to learn the best possible policy that always gives me the most value out of every board position, out of every state. And that's a really hard problem. It's easy to state the goal, and it is really, really hard to solve this problem. That's why it's been this growing field for 100 years. That's why it's still a growing field, because we have more powerful emerging techniques in machine learning to start to solve this problem. So that's the framework. I need you to know what the policy is. That is the set of kind of rules or controllers that I as an agent get to take to manipulate my environment. The value function tells me how valuable it is to be in a particular state. So I might want to move myself into that state. So I need you to know kind of this nomenclature, so now I can kind of show you how all of these techniques are organized. Okay, so that's what I'm going to do for the rest of the video, is we're going to talk through kind of the key organization of all of the different like mainstream types of reinforcement learning. Okay, so the first biggest dichotomy is between model-based and model-free reinforcement learning. So if you actually have a good model of your environment, you have some Markov decision process or some differential equation, if you have a good model to start with, then you can work in this model-based reinforcement learning world. Now, some people don't actually consider what I'm about to talk about reinforcement learning, but I do, okay? So for example, if my environment is a Markov decision process, which means that there is a probability, kind of a deterministic probability, that sounds like an oxymoron, but if there is a specified probability of moving from state S to the next state S prime, given action A, and this probability function is known, so it doesn't depend on the history of your actions and states, it only depends on the current state, and the current action determines a probability of going to a next state S prime. Then two really, really powerful techniques that I'm going to tell you about to optimize the policy function pi is policy iteration and value iteration. These allow you to essentially iteratively walk through the game or the